Welcome back. In this video, we'll introduce two more discrete distributions, the negative binomial distribution and the hypergeometric. So we'll start by introducing the negative binomial distribution, its definition, and some properties. We will also introduce the hypergeometric distribution, talk a little bit about how it's different from the previous discrete distributions. And then finally, we'll look at how to find probabilities related to both. So let's jump right in. Starting with the negative binomial distribution, we say that a random variable, apologies for the typo, this x should be a y. A random variable y follows the negative binomial distribution with parameters r and p if the following. The probability that y is equal to little y is equal to y minus 1, choose r minus 1, times p raised to the r times 1 minus p raised to the y minus r. We have two parameters in this distribution. R starts at 1, 2, goes up to y, and then y starts at r, goes on possibly infinitely. We say then that y is distributed negative binomial with parameters r and p. So what is this distribution good for? What on earth could this thing possibly represent? Well, the negative binomial distribution is a little bit like the geometric, just extended. The negative binomial distribution represents the number of trials it will take in order for us to find our successes. So let's see how we might use this distribution. We have applicants for a new student internship that are accepted with probability 0.15 independently from person to person. Now the way we're going to review these applications is a little bit different. As soon as we hit one application that is successful, that person is in the program. They're a success. We'll continue reviewing applications until we find at least 10 students for the program, until we've filled all 10 spots. What we'd like to do is find the probability that it will take no more than 10 applicants to find 100 students. So y will be the number of applications we need to review until we find those are successes, those are students for the program. Y is then distributed negative binomially with target number of successes r, probability of success 0.15. So in order to find the probability that y is less than or equal to 100, where does y start? Well, the smallest number of applications that it will take to receive or find our successes is r itself. So the lower value for y in this situation is 10. So what we want to find is a summation from 10 to 100 of 100 minus 1, choose, this should be I minus 1 in the summation, 0.15 raised to the I times 1 minus 0.15 raised to the 100 minus I. So when you see a 10 here, replace it with an I throughout the summation. This summation is going to have 91 terms. I don't want to calculate 91 terms by hand. I'm sure you don't want to calculate 91 terms by hand either. So there has to be an easier way to do this. In R, we can use the n binom family of functions to help us calculate these probabilities. Given our experience with the geometric though, it's probably best to just try an example to see whether or not this is parameterized the way we think it should be. So let's start by finding the probability that we find the 10th success on trial number 11, the probability that y is equal to 11. Plugging into our formula, we get 11 minus 1, choose 10 minus 1, times 0.15 raised to the 10th power, times 1 minus 0.15 raised to the 11 minus 10 of first power. Calculating that out, I get a very small probability, so it's highly unlikely that we'll find that 10th success on trial number 11. However, it looks like R isn't thinking about this problem the same way that I am. Their value does not match what we calculated by hand. Like with the geometric, we're looking at the number of failures that we'll observe before the rth success. So if y is equal to 11, we observe 10 successes on observation or trial 11. That means that there was one failure. So here we'll use y minus r in our first argument to match our parameterization. So another example where things can be a little bit trickier than they seem. Okay, so let's let y then be the number of applicants needed to find those 10 students. Here's our summation that we want to look at, 91 terms. We don't want to do by hand. So we'll use that cumulative probability function in R. So we want to find the probability that it takes up to 100 observations or 100 applicants to find 10 successes. Because we've parameterized things differently, our first argument is the target number of trials, 100, minus the target number of successes, 10. Size is 10, that's the number of successes R, prob is 0.5. There's about a 95% probability that we will find 10 students in 100 applications or less. So here is what this negative binomial distribution looks like. In lighter blue, I've shaded all of the possible outcomes or all of the possibilities under 100. So we can see that most of the time it will take 100 or fewer applications to find those 10 successes. Okay, so for this distribution, what's the expectation? What's the variance? The expected value of a geometric random variable is the the expected value of a negative binomial random variable, of which the geometric is a special case, by the way. Expected value of a negative binomial is R over P, so the target number of successes divided by the probability of success. The variance here is R times 1 minus P over P squared. So let's find the expected number of applications that we need to review before we find 10 suitable candidates. Our expected value is going to be R over P, so 10 over 0.15. We'll need to review about 67 applications to find our 10 applicants. Now let's take a look at one more discrete distribution, and this one's a little complicated. So suppose that there are R special objects, or objects with some characteristic that can be selected from a finite population. So we have capital N total members in our population. We're going to take a sample of little n members of the big N population. We'd like to know how many members of the sample are special, meet that characteristic that we care about. This can be described using the hypergeometric distribution. So the probability that there are y objects or y members of a sample with this special characteristic is R choose y times n minus r choose n minus y divided by big N choose little n. Think about what this is really looking at. In the denominator, we have big N choose little n. So this is the number of ways to choose a sample of size little n from a population of size big N. We'd like to know how many of the observations are coming from that group with the special characteristics. There are R of those. So we'll take R choose y. All of the other elements of the sample are non-special in that other group. So that's where the big N minus R choose little n minus y comes from. So this is a distribution that we can actually sort of back solve if we know a little bit about what these numbers are representing. So let's take a look at an example. Suppose there are 100 political independents in a student body of 1,000 students. We're going to take a random sample of 50 students. What's the probability that we get fewer than 3 independents in the sample? So here is what this looks like. Y is a hypergeometric distribution because we have a fixed population size. That fixed population size is capital N or big N, so big N is 1,000. We're going to take a sample of 50 students from the full population. In the full population, 100 students are what we would consider to be politically independent. So that's where the R equals 100 is going to come from. So the probability that y is less than or equal to 3 is the probability that y is equal to 0 plus the probability that y is equal to 1 plus the probability that y is equal to 2 plus the probability that y is equal to 3. So we've got 4 values that we'll need to add up. In terms of the probability mass function, here is what those calculations will look like, just plugging everything into the appropriate values from a hypergeometric distribution. And we get about a 24% probability that there will be 3 or fewer independents in our sample. Now, like the geometric distribution, like the negative binomial distribution, the way that our textbook defines things is a little bit different than the way that R defines things. So what you're seeing here, I've actually taken advantage of vector notation in R to calculate multiple probabilities at once. So it turns out that in most R functions, you can feed in a vector or a list of values, and R will carry out the calculation for every member of that list. So for example here, where I write choose 100, comma 0 to 3, what this is doing is calculating for all of the integers between 0 and 3 inclusive that choose. So choose 100, 100 choose 0, 100 choose 1, 100 choose 2. So I can calculate all 4 of the probabilities at the same time using this, which is pretty neat. I can do the same thing in the hypergeometric probability function. So here I'm using d hyper to calculate the distribution from a hypergeometric. The m argument refers to our r argument, so that's the number of special elements. N refers to the number of non-special elements in the population. So here that's 1,000 minus 100. K is then our target sample size. So we just have things written a little bit differently. We can use the sum function to add all of these up, or if we're using those probability functions in R, we can use the P to get a cumulative probability. Now, when you're not sure how R, or really any computing language, is calculating something or defining some distribution, try using a reproducible example. Try doing what we have just done. Pick a problem that is reasonably simple to calculate by hand, calculate it by hand, play around with this new function that you're learning until you can reproduce the example. You do not need to throw your computer at the wall. It is okay. We'll figure out how all of these are working. But in my experience, one of the best ways to really learn how a function is working is just play around until you can reproduce an expected output. Okay, so let's talk about properties of the hypergeometric distribution before we finish this video. The expected value of the hypergeometric, so the expected number of special objects in a sample, is n times r divided by big N, the population size. The variance is complex. I will let you guys read that variance formula on your own. That's a long one. So suppose there are 100 political independents. We have our random sample of 50 students. Let's find the expected value and the variance of the number of independents in that sample. So our expected value is n times r over big N. So we've got 50 times 100 over 1,000. We would expect to see about 5 independents in that sample. The variance is about 4.3. So we would expect some variability from sample to sample. We have one more discrete distribution to introduce. That is the Poisson distribution. And we'll do that in the next video. See you then.